Now, the second part is about two given series, which are at first sight not easy to handle. The question is, do they converge? It's not, we are not asked to calculate the limit, which may be hard to do, just about convergence. So this one at first sight, hard to say. This one, well, if you know it, you may know that it converges. But anyway, there's a hint which says apply the comparison test by using what we call a minorand or majorand, and then decide by yourselves, in the ideal case, where a minorand and where a majorand will make sense. Well, respectively, okay, as follows. And now these two series are proposed to be used as minorand or majorand. Well, the first idea should be perhaps have a look and compare these candidates here with the original series here and here, where, well, if you find a similarity, you should do the pairing accordingly. I would really say that these ones correspond a little bit to each other, and also these ones. If you just see that this is k squared, and if I, well, either if I remove the parentheses, then getting 1 by k squared minus k, so there's, it seems to be almost the same. Or if I say, okay, this is a number times itself, and this is a number times its neighbor number. So there's quite a similarity. Anyway, let's start with the harmonic series. And that's why this is given here. This is probably the most famous series of all. And it's called the harmonic series. And we all know, or you know at least, and you even proved it in the lecture, the sum of 1 over k, k running from 1 to infinity, does not exist. It means that the harmonic series is divergent. This can be proven in different ways. There's quite an interesting way by, yeah, you know how it's done by grouping these elements and then showing that you can, as often as you want, you can produce a contribution of 1/2. So in the end, it's transformed to something like 1/2 plus 1/2 plus 1/2 and so on forever. So that's a fact. It's divergent. If it's divergent, please note, it can only, of course, be used as a minorand. Why is it? Because the comparison test only offers you two interesting possibilities. One of them is to find a divergent minorand, and the other is to find a convergent majorand. So that's the combination. You just have to yes, just hammer it into your brain. Yeah. So never forget it. Divergent minorand or convergent majorand. These are the only two cases which make sense. So that's a fact. Now, let's just suppose that this will be, in the end, will be the divergent series, or a divergent series. It might be the case that this one is useful as a divergent minorand, but then we would have to show that these elements inside are always, as it says, why it's called minorand, are always lower than these ones. And so that's what I claim. And I take a little care about really proving it, okay? You might say, yes, of course it is. But I say the claim is 1 divided by square root of k is greater or equal to 1 divided by k. So 1 over square root k greater equal 1 over k. That's a claim. You might say, okay, take an example. If k equals 100, I have 1/10 is greater or equal 100th. Of course, that's true, so that's it. But I want to make it a little more precise. What do? I take this unequation and take the reciprocal on both sides. So by inverting these fractions, taking the inverse or the reciprocal, I get square root k here and k here, but I have, now it's important, since taking the reciprocal is a descending operation, it's even a monotonously descending operation, it means let's say, large numbers are transformed to low numbers and low numbers are transformed to large numbers. Since everything's positive here, the argument goes as follows. Due to this descending operation, I have to change the comparison sign. That's very important. So now it means that root of k lower or equal k than k. Now, again, you could say, yeah, that's obvious, so let's do it. No, I still want to make it clearer. I square this equation, and by squaring, I get k here, and then lower or equal k squared. Now, in the next step, even, I divide this, and I may divide this by k, which is positive, and there's no reason to change the comparison sign this time, also here, no, not. This is not an equivalence transformation, as I know, but that does not matter to for our purpose, okay? Because we just want to prove that this claim is true. And what anything that follows from this claim will be a valid result. Well, let's say, let's look. If it's unambiguous in the end, the squaring did not make any harm. So anyway, dividing by k by k is 1, and here k squared divided by k, since k is positive anyway, element n plus, this is what I use for denoting the positive natural numbers, excluding the 0, which is sometimes counted as a natural number, sometimes not. So I have 1 lower or equal than k, and then if I change the sides, I have the result that k greater or equal than 1. And now it's fine for me because I can say the prerequisite was, or yes, the premise was that k is element of n plus. K is greater or equal than 1. That defines the positive natural numbers. And since that is our result, it means that this is actually sort of like a tautology. So it's true just by using the natural numbers. It's automatically true. So now that's fine. Okay. Anyway, we have just shown that the harmonic series is a valid divergent minorand to this series, so this series must also be divergent. That's all, actually. And now let's proceed to the other one. And this will be a little more of work, but it's very interesting. I can tell you that this is a very famous series, which was even centuries ago, it was well known that this series should be convergent. But at the time, nobody was able to find an analytic expression for its limit. And it took some decades then, around 18th century, something like that. It took some decades until Mr. Euler came along and made one of the most elegant proofs ever to prove that the limit of this series is actually equal to pi squared divided by 6. And this made the people of that time, well, giving him standing ovations, really, historically. Because when he presented this result on a mathematical conference, it is said to have been the shortest mathematical talk of all times. It consisted of Leonhard Euler standing at the board and writing down this equation, which meant suddenly he has found a proof, obviously, because nobody could have guessed even that the circle number, the magic number of circles, pi, appears in the limit of a reciprocal squared series. This is something about squares. This is about circles. And the saying, not completing the square, but transforming a square into a circle. It's in German, it's called Quadratur des Kreises. It's transforming a circle to a square, actually, which is said to be impossible. So there seemed to be no connection between squares and circles. But now suddenly there's a very, very tight connection between the two. So that's just about the background of the whole thing. But now let's look. And this one looks very surprisingly similar, or not surprising, strikingly similar to the one we had in the previous section. But it's unfortunately it's not quite the same. You see, this is important to really take a close look. This is a summation starting from 1 to infinity, and then we have 1 by k times k plus 1. Here, on the other hand, look at this. This is very easy to overlook. The summation takes place starting from 2 going on to infinity, and then we have k this time times k minus 1. So it will be a little tricky to show that this one is essentially the same as the one before, where we could show that this is bounded. So that it means that it's first of all, it's convergent, and the limit is 1, by the way. So if it's convergent, we can use it as a majorant. That's a prerequisite for using it as a majorant. And then even we would have to show that it is, well, that it is a majorant, this series. Okay, let's start. And actually, oh, sorry. Yeah, now it works again. Yeah. I forgot to say, just back for a second to the other one. It's quite interesting. If you forget everything about here, a minorant or a comparison test, it's striking if you put your series from before, the square root, reciprocal square root series, just put some of the elements here. So it seems to be s equals 1 plus, then 1 by square root of 2 plus 1 by square root of 3. And then as soon as I reach plus 1 by square root of 4, I find out, aha, each time I have a squared number under the root, I can take the root so that it gets rational. Then I get a contribution plus 1/2. And it goes on, plus 1 by root 5, plus 1 by root 6, and so on. And every time I reach a squared number under the root, it gets rational. So what is this? It means that every single element of the harmonic sequence is contained in this series over this reciprocal square roots sequence. And that's even a valid proof to say, of course, if even the blue members here, the blue contributions summed up to infinity are divergent, then the square root, reciprocal square root series, of course, must be highly divergent. So that's almost nicer even than the comparison test, but that's just by chance now. Okay, so you could say this is an enriched version of the harmonic series. Okay, an enriched version because more than these elements are inside. And interestingly, this one here is the opposite quite. It's called, sometimes it's called a dilution of the harmonic series. You know why? It's because look at the first elements. It's like 1 plus 1 by 2 squared plus 1 by 3 squared and so on, all the squared numbers here. So it's 1 plus 1/4 plus 1/9 plus 1/16 plus and so on. But this means that these elements, all of them appear in the harmonic sequence, of course, but summing them up means that just the diluted version of the harmonic series comes along here. It's many of the elements of the harmonic sequence are missing. And that's why such a series has, at least it has a certain chance of converging in contrast to the harmonic series. If the harmonic series, and since the harmonic series diverges, it might still be that such a diluted version of the harmonic series is convergent. And as we will see, this one does converge. So that's quite interesting. Now, the comparison series is this one, as it's given. Let's look at the elements. They are just putting the first of them, first 3 elements here, that's enough. So I have 1, it starts with 2 here. So I have 1 by 2 times 2 minus 1, which is 1 by 2 times 1. And the next element is then 1 by 3 times 2, and then plus 1 by 4 times 3. If you remember, these are exactly the same numbers as in part 1. It's equal to 1/2 plus 1/6 plus 1/12 plus and so on. But remember, or just note that the order of the factors is different here. Look here. Here it was given as to be 1 times 2, 2 times 3, 3 times 4, and this time it's 2 times 1, 3 times 2, 4 times 3. Of course, it's the same, but you see there is a little structural difference between these two series. But you can now also understand why the summation index k starts only from 2 now in our new example. It's just to achieve an exact equality between these two series. Okay, leaving away, you could say, the first element of the other one means that all the contributions are exactly the same. Now, the trick is, if you want, I can transform this also, but differently than before. Well, how do you do it? What's the best method? Well, it doesn't matter. We could say, a little clumsy now, we could say, okay, obviously these are the same elements, so, and we have already proven that this has a limit of 1. Let's do it this way, okay, for brevity, for shortness. So our sum of our of this one, okay, of this reciprocal squared series will be 1. Why do I say 1? Well, I just take away the first element. You see, when k equals 1, I have 1 by 1 squared, which is 1. Here, you see it here, the first one. I separate it. If I separate it, I can continue the summation starting from k equals 2. And that's what I'm doing. I put the 1 isolated here, okay? The first element, where am I? Sorry, here. First element 1, plus then summing up only starting at k equals 2 up to infinity, 1 by k squared. And now I construct an unequation and say this will be lower or equal than taking over the 1. 1 is 1, okay? I just take the same number, 1. But just looking here, since I know, do I know? No. I do state that this every single contribution here of this series in comparison with the contribution here will be lower or equal. And why is it? K squared is quite obviously larger than k times its predecessor. You know, example, 8 squared is 64, and here 8 times 7 is 56. So the reciprocal of 64 is lower than reciprocal of 56. That's clear. Okay, in general, it's clear. So since this is a convergent majorant to this one now, since but only since we adapted the starting value of the counting variable. Yeah, so then it's a convergent majorant. And now the question, which limit does it have? And now it's time to transform it formally to the one we had before. How do I do this? Well, I make a little substitution. The substitution is L equals k minus 1. In other words, if I isolate k equals L plus 1. That's what I do. Look here. If I replace k by L plus 1, I have L plus 1 equals 2 as a starting value. Then, of course, running to infinity also makes no difference. Okay, both are running to infinity. But then replacing here 1 by k replaced by L plus 1, and k minus 1, of course, here replaced by L. You see, times L. And now, okay, that's a little complicated. I took k to be L plus 1, and then I subtracted 1. But anyway, I could have used this one also. Anyway, it's L in the end. So what do I get? I get, isolating L here, L equals 1 as a starting value up to infinity, then 1 by L plus 1 times L. And now, if I call it L, or if I rename it to be K, it doesn't matter. It's structurally and arithmetically or algebraically exactly the same series as in exercise 4.3 part 1. So now we can correctly state that this has a limit to be equal to 1. No, I used it in this form to be a majorant anyway to this one, but to show that it is convergent, I put it in this form and then confirmed that its limit is equal to 1 even. That means we can not only say that our reciprocal squared series is convergent, we can even give quite a good approximation of its limit. Why? Because you see, if the first element is 1, the limit can, these are all positive contributions, the limit can in no way be lower than 1. So the minimum value of the limit will be 1. But on the other hand, the whole expression is lower or equal than 1 plus the limit of this one, which is 1 plus 1 then. So this is 1, okay, limit is 1, 1 plus 1 is 2. So that means that the limit of our series must lie between 1 and 2. And that's quite interesting because, as I told you, the famous proof by Euler showed this is really a very wonderful proof. You might look it up you find it on the internet if you just do a little research, search for it. S equals pi squared divided by 6. And you know, there's a very good approximation for pi squared, which I sometimes use, which is it's almost equal to 10. You know this? I think we used it before. 10, take the square root, and you find 3.16. So that's an approximation which is it has an error of, say, perhaps 1%. Not much more, or some percent, really. So this is almost equal to 10 by 6, which is again 5 by 3, just to confirm that the true limit of this series lies between 1 and 2. I found this quite nice to see.